normality test, box plot, bar chart, and t-test. How to perform these analysis in BioStat Prime. Let's open the BioStat Prime software. So remember in the last video, we have working with this particular data set and we converted from wide format to the long format. So now you can see this one is a long format and the first column here is a concentration. So just left side of the concentration 1, 2, 3, you can see that means this one, this whatever the value that we have is numerical, right? And then this is the grouping variable or factor. Well, there are two groups we have, or two factors we have, the drug and placebo, right? So those are known as level in standard statistics. So well, you can also click on to the variable to have a look at these variables. So you can see concentration is a numeric variable while treatment is a factor variable with integer, and the levels of this factor variable is drug and placebo. I hope it's clear to you. You don't have to change anything, right? Now we have this data. Now this is in long format. It's ready to go for an analysis inside this BioStat Prime software. So first analysis that we are going to do today is that we have to see that is it actually comes from a population that follows the familiar bell-shaped distribution of the normal distribution. So to click to test the normality, that so-called normality test, there are two options for you. First option is that inside the analysis, distribution analysis, there is a drop-down menu. You can choose any of these tests, including Anderson-Darling test, Kolmogorov-Smirnov test, Shapirov-Wilk, or there is another option here. Inside the movement subsection, there is a drop-down menu. There is an option called Diagostino-Skewness test. Formally it's called Diagostino-Pearson K-squared normality test or skewness test, because it depends on skewness and kurtosis. Now, because this test depends on kurtosis, kurtosis works best if your n is more than 20. So though this test is really good, so those with n less than 20, in this case, as you can see, n is 17. N means sample size, total number of elements in our data set. So there are 17 elements in our data set, and therefore this test is not really good. For 17, the best test is our Shapiro-Wilk normality test. So let's do it. Shapiro will click onto it, and numeric variable, which numeric variable? Of course, the concentration is our numeric variable, and just click run. That's it. Then it's going to return the results on your right side. And as you can see here, the p-value is the most important. 0.5192 is pretty high p-value. The interpretation is straightforward. Of course, you need to know the basics of statistics in order to make out of this p-value. So the p-value is higher than our cutoff p-value 0.05. That means that this, there is no significant differences from our assumption of the normality. That means this test passed the normality test. So in normality test, whatever the test that you do, getting a high p-value higher than 0.05 cutoff, that is 95% confidence interval, is always preferable. So here the interpretation is that this our sample did pass, our data set passed the normality test. So that means we can go ahead with parametric statistical analysis like the t-test, no problem, right? Okay, now let us do graphing with this software. So I'll just show you inside the graphics menu. This is for the data visualization, right? Like generation of the graph. Let us generate a box plot. Very simple box plot. Box plot is basically a non-parametric. No problem. Non-parametric is okay with parametric also. Even if our sample comes from a normal distribution, box plot is absolutely fine. So once you click the box plot, it will ask you the parameters. Of course, the first one is numeric variable. Just choose the numeric, and then X variable, the category variable. Here the category variable is the treatment, And that's it. You can play with any of these options, and a lot more options are there. If you click on to the options, then phase sets, and then scroll down to the add reference line, well, lots and lots of things. This software is really powerful. So for the sake of brevity, we'll skip all those fine tuning of the box plot. I'll run it. So click on to the play button. On the right side, you get it. Yeah, you can see that there is box here. It's a vertical box plot. And in this box, you see the top edge of this box is at 75th percentile, while bottom edge is at 25th percentile, the first quarter and the third quarter. And the line is at the median. So you can compare. So you can see that the drug concentrations are much higher than the placebo concentrations, right? So that is what it means. Well, now let us also generate the bar chart. The same way, click onto the bar chart, and then X variable is our treatments, while Y variable is our concentration. And then, well, you can just click onto it. What kind of bar chart do you want? You want count, that is your primary data bar chart, the whole data it will be presented, or you want mean is commonly used, right? So mean plus error bar. What kind of error bar you want? No error bar, or you can go with confidence interval. Yeah, confidence interval makes sense if you're comparing the means, right? So let us go with 95% confidence interval without changing any in the options of phase set option. So I click here, run the play button. So well, you can see the bar chart has already been generated with the error bar. So the height of the bar is exactly at the mean, arithmetic mean or average, right? So as you can see, the average of drug is higher than average of the placebo. Now there is error bar on both sides with tick mark. So this error bar represent 95% confidence interval. So as you can see, this 95% confidence interval do not overlap. You can visually inspect it. You can zoom it by clicking right here, lower right side, zoom to 125, or well, more you can put, 150, let us say 150, and inspect it. So well, there is no overlap. So instantly you can conclude that the p-value must be less than 0.05, and the differences between these two groups are significant as per the standard statistics. You can check the basic module, isn't it? All right. Now finally, let us perform the t-test, students t-test. How will you do it? Click on to analysis, and all different kind of analysis is there. We are comparing the means of these two groups. So means drop down menu, you can click t-test independent sample. Well, there are many other options like ANCOVA, ANOVA, MANOVA, and different incarnations of the t-test too. Let's stick with t-test for independent sample. In our case, it is independent sample. I click onto it, then select the variables. So that is our concentration, and the treatments are our two levels of factors. Now, what is our alternative hypothesis? Is that drug 1 or group 1 is equal to the group 2? Means of both are same. So this is a classic example of the two-tail p-value, right? The other two are for the one-tail p-value. So we'll stick with the first option, and you can override this confidence interval to from 95 to 95% is more or less arbitrarily fixed for biological sciences. So you don't really have to change it. Well, effect size for displaying the effect size, coherence, bias correction, or hedges correction, or glass correction, delta, right? And options for the missing values and Levene's test, all those things you can tweak in case you are interested. Otherwise, just click the play button to run it. So the test will be ran. Here you can see this is a group statistics, and the most importantly, you have to look at the sigma, and that also two-tail sigma, the p-value. Well, these are sigma is nothing but p-values. So there are two types of p-value presented. One-tail p-value is the first one, and two-tail p-value is the second one. Disregard the one-tail p-value. This column, the one-tail p-value, just doesn't matter at all, this one-tail p-value. Okay, so you don't have to worry anything. Never report it. That is a consensus of the statisticians around the world. So no matter what, never report the one tail p-value. Just stick with this two tail p-value. So looking at the two tail p-value, two tail p-values here. The first one is assuming the equal variance. The second is assuming non-equal variance. So equal variance is not assumed, right? Unequal variance. So it doesn't matter whichever. So the first one is always better equal variance assumption, or you can also go with the without that assumption. Well, this is much more relaxed. This is also absolutely fine. So you can see that the p-value is with 2 star. That means it's significant, isn't it? There are 2 star here. 0.0028 is the p-value of our t-test. That means our two groups are significantly different. So the differences are statistically significant. And it says the same with our first conclusion that we arrived by comparing the bar plot, isn't it? 95 percentage error bar, there is no overlap. So we already concluded, and this result validates our conclusion arrived in our confidence interval, 95 percentage confidence interval comparison of the error bar of the bar plot, isn't it? Here, this is what our initial conclusion, and this validates it, this p-value, right? So this is yeah, in a nutshell, this is how to perform the normality test, and also how to generate the graph, like the box plot, or this the bar chart, and also how to perform the analysis. So to explain a little bit further, here the box plot, if you want to tweak it further, if you want to do it with some extra parameters, you can just click onto it. This parameter window will come, and you can just change anything, and then you can rerun it. It will be appended, or this result will be changed into the new one. Okay, so this is how to do that. And also, if you want to use this diagram for your publication, how will you do it? Just right click onto it, copy the image and paste it onto your paper, or you can download as SVG or PNG, and then submit. When you when you upload your paper separately, this image needs to be uploaded separately for most of the standard papers and reports, isn't it? So this is how to do that. And also, if you just want to clear all these things, well, this is a table. The table also you can just click and copy as text, or copy and then paste it elsewhere. And if you want to save this output alone, that is this option here, and now export the output and clear the output, just delete everything and just close this output. All these windows have different options. And also on this box plot analysis, instead of running, you can just click onto this to show the R syntax. If you know R already, you can tweak the syntax option of the R. And also, if you have no idea about the box plot, to learn what box plot is, you click on this interrogation mark and read it, what the box plot is all about. And further information, if you want to learn, then you can click on to this thing, the help in the window, so that way you can do it. So once you're done, you can just say, you can just close this parametric window, the box, so that you will be taken back to our independent t-test data. This is our the data set. Well, you can save this data set as a Prism file. How do you save it? To click onto this file and then save as a project. So I strongly suggest you, before closing anything, save as a project file. Okay, so click onto the save project. It'll ask you what name you want to put it. For example, t-test. And let us save that in the default project category that will be inside the C app data of your BioStat Prime project. So everything is now crystal clear. It is just saved. Of course, you can override it and save elsewhere too, and just click save. So now everything is safe. Now I can close this window to exit the BioStat Prime. Thank you.